Hello and welcome back to PC Retro Programmer. In the past couple of videos on the channel, we've been trying to get a linearly addressed graphics mode for CGA, just for fun of course, not for anything serious, but also to try and learn as much as we can about the CRTC. And due to various glitches that we're encountering with the CRTC, this is proving to be more difficult than one might initially imagine. This is the way things looked at the end of the previous video, and there's quite a lot here that needs explaining. The most interesting region, of course, is the magenta part. We have 16 magenta scan lines interleaved with 16 cyan ones. And the reason this is happening is most likely because the CRTC is doing a single character row of 32 scan lines per character, the maximum possible value. And the reason that's happening is because we're setting the maximum character scan line to 0 at a point where we're already on scan line 1 of the current character row. And so it then has no choice but to keep counting up from there to the maximum possible value in that register, which is 31, before it'll wrap back around to 0 and finish the current character row. Now, we tried to take steps in the previous video to prevent this from happening because we surmised that it was causing a loss of sync that we observed. We got rid of the loss of sync, but clearly this problem is still there. Now, the reason is most likely due to a timing issue. We're probably writing register values at the wrong point. We need to do them within the bounds of the correct scan lines, otherwise the CRTC gets itself into a completely different state than the one that we intended. And this actually explains why we have these two vertical blanking regions at the top of the screen. When you start this effect up, the CRTC briefly loses sync until it settles into some kind of stable pattern, albeit not the one that we were aiming for. So in order to fix this, we need to figure out why those register writes aren't happening at the right time. And in order to help us do that, we're going to use the background color, which we're going to change at the point where those register writes are supposed to be happening, so that we can see where on the image, in other words, where in time, those register writes are actually happening. And if they're not happening within the bounds of the correct scan line, then that'll explain the problem. I've already written some code to try and figure out what's going on here. And this is now linear9.ism. It's the same as what we had in the previous video, except that on raster line 127, instead of breaking it up into two shorter scan lines, I'm actually going back to having a single wide scan line. Now, this is a trick that you can use to get to the bottom of timing issues. Basically, what you do is you do all the same register writes as you would do to set up your weird, wacky video mode that you try to program, and you do them all at exactly the same position. But instead of actually changing the register values, what you do is you just leave them as their current value. So for example, horizontal total at this point is already 56, so changing it to 56 shouldn't, in theory, change the screen geometry in any way. And similarly, the horizontal displayed is currently 32, so changing it to 32 won't do anything, and so on. So all the register writes will still occur, and this allows us to separate timing issues from screen geometry issues, which of course we've been having. Now, I have to point out one caveat here, and that is that some of these CRTCs actually have side effects just simply from setting a value in a register, even if you set that register to the value that it currently has. Now, this is a rare thing. It only happens in very specific circumstances, but it is something to bear in mind that these CRTCs are really glitchy, and even setting a register value to what it currently is can actually mess things up. Fortunately, that's not going to be a problem for us today. Now, our hope is that we're going to be able to check whether these three register writes here get done before the end of the active region of raster line 127. So immediately after doing those three register writes, I'm going to change the background color here to 12. This is a bright red color, and I do that just by setting the background color in the color control register of the CGA, which is port 3D9H. I actually have to put the value 2CH in because this register also controls the CGA palette and the intensity. I've just chosen the standard CGA palette here of cyan, magenta, white, and I'm actually using the low intensity palette just so that that bright red background color shows up more clearly in comparison. So what we should see on the screen is the background color change from black to red at the precise moment when these three register values have been updated, and that should allow us to confirm that it is in fact happening within the active region of raster line 127. And likewise for all of the other portions of these scan lines, I'm doing the same register writes as I had at the end of the previous video, but again, I'm just leaving the values exactly as they are, not changing them, so I don't have to worry about screen geometry. The other thing I have to do, of course, is to set the background color back to black at some point, otherwise the entire screen will have red as the background color and we won't be able to see where that starts. So a convenient location to do this is raster line 129, a couple of raster lines later, where I set it back to color 0, which is black. So let's go ahead and assemble this code and see whether or not it allows us to get to the bottom of our timing issues. Let's see if we even have this thing in sync. And it looks like we do, and you can see that the red line where the background color is being changed starts way over on the right hand side, past the end of the active region. So this is already a bit worrying. Maybe we're not actually getting all of our register writes done in the active region for that first portion. So let's try and confirm whether or not that's the case by starting the red line where the final write to a register would be done in that active region. To that end, I've changed the code now for raster line 127 to this. I've commented out the horizontal sync position register change, and so that's no longer happening, and I've replaced it now with the background color change. Now this is not an exact science. You can see that I have to change the DL register here and not here. I'm changing the AL register here, but the AX register here, and I'm doing an out DX AX here and out DX AL here. So these are not exactly the same, but to a first approximation, this is going to show us where this horizontal sync position register was being changed on the scan line, and should allow us to confirm that it happens before the end of the active portion. Well, let's see if this is any better. And yeah, it looks like we're occasionally getting the background color change in the active region, but quite a lot of the time it's happening just after the end of the active region. And at first glance, this might seem bad because it implies that the register write that we were doing at this position is happening too late. But it actually isn't an issue per se. And the reason is the register write we're doing here is for the sync pulse position, and we're setting it to a value of 12, which corresponds to a position right over the right hand side of the screen. And so long as we do that register write before we actually reach 12, then it shouldn't be a major issue. And clearly that is actually happening. But something that is bad is that the polling for the non-active region is clearly starting very late. It has to happen after this point, and so that means that we don't know whether or not all of the register writes in the non-active region are getting done in time. So I think there are two things that we can do here. The first is to move that register write for the sync pulse position earlier on the line, and that's actually very easy to do. We had a delay in there before that. There were some no-ops that we inserted. We can just remove those. It's very clear now that we're not at any risk of having that register write happen too early. And the other thing that we need to do is to check whether all those register writes in the non-active region are getting done in time. Once again, by using the change of background color after the end of those to see whether that's happening before the next scan line starts. I've made those changes to the code. Here you can see in raster line 127 there's now no delay, there's no ops between the second and third register right here. So this sync position register is being changed immediately after the first two, and I've now removed the change of background color, and I've put that further down in the non-active region now, so we can check whether or not this final register right here, which I've now commented out, was happening before the end of the non-active region. And so we can go through the code step by step like this, figuring out where all the register writes happen and making sure that they all happen at the right point. Well, let's take a look and see what's happening. And yeah, that register write is occasionally being done before the end of the non-active region, but it's quite often happening after the start of the next scan line. And this is really not allowed. All three of the register writes that are supposed to happen in the non-active region have to be done in the non-active region. If any of them happen late, then it's going to screw up. So this is almost certainly our problem. So now that we know what the issue is, let's try and find a solution. Let's take a look at the code that I've written to try and fix all of this in linear.a.asm. I've got rid of all the code for changing the background color, and I'm back to actually changing the register values to try and get into the linearly addressed mode. So we'll focus on raster line 127, where we were having a clear problem getting enough done in the non-active region. So one way that we can try to improve things is to cut down the number of cycles it takes to do the register writes. Now, we had 3 register writes to get done in the non-active region, and instead of moving immediate values into the AX register, what I've done is preload some values into some of the other registers, BX, SI, and DI, so that I just have to do a register-to-register move instead of moving an immediate value into AX. So I preloaded those 3 registers above here. This is actually really at the end of raster line 126, where we have some spare time. And that should cut down the number of cycles that it takes to do the register writes down here in the non-active region of raster line 127. Now, it turns out that this is still not enough. We still don't get those 3 writes done before the end of raster line 127. So in order to save even more time, what we have to do is axe the polling for the start of the non-active region. This is actually really expensive. As I explained in a previous video, this takes about 25 cycles per iteration. And if we just miss the start of the non-active region, it goes all the way through that iteration and has to jump back to here to do another iteration before we have detected that we're in the non-active region. So it can actually be almost 50 cycles to do that polling. And if we set things up so that we're already just at the very start of the non-active region here, skipping this will save us almost 50 cycles, which is almost half the time that we have in the non-active region. So this has actually been our problem all along. So ironically, the solution here was to put our delay back in the active region before the write to change the horizontal sync position. And that pushes this out until we've almost started the non-active region, or in fact just started the non-active region. And so by this point here, we can be absolutely sure that we're already in the non-active region, so there's no need to poll for it. So that is basically the solution that we're going to try. So let's check it out and see what happens. So we'll just assemble this, and then we'll run it on the real hardware again to see how we fare. Well, let's see if we finally have something. And yeah, this is looking a little bit more encouraging. First of all, we're clearly getting some data from the second bank, but unfortunately it's not from the first scan line of the second bank. We're getting data from the end of the second bank. You can see it's magenta, not white. So that is an issue that we're going to have to look into. The next thing you can see is that the final cyan scanline before that is 1 byte too long. And it turns out that this is actually due to a glitch in the Hitachi CRTC. It also happens with the Motorola CRTC, by the way. Under normal circumstances, we'd have a value of horizontal displayed that's less than horizontal total here. So it would go along, it would reach horizontal displayed, stop outputting characters, and then continue until the end of horizontal total, or actually one more than that. And of course the Hitachi CRTC is designed to blank the final character. So with a horizontal total of 32, as we currently have it here, we'd expect the final character to be blank, and that final character would line up with where that extra blue bit is. But this only happens, as it turns out, if you've actually already hit horizontal displayed on this scan line, and we actually haven't. At the moment we have it set to 0, ready for the start of the blank scan line on the right hand side of the screen. And so from the CRTC's perspective, that's a wraparound. So it hasn't actually reached that value yet. It really thinks of this as being bigger than the horizontal total value, and this causes a glitch in the CRTC. Instead of blanking the final character, it displays this kind of half character and half a blank character. So that's the explanation for that, and we're going to have to try and find a creative way around that. And the other thing you can see is that there's a flashing black section in the middle of our magenta line, and clearly this is due to a horizontal blanking period. We have a sync pulse firing in the middle of the screen, and this is something that we can probably easily fix. It's just because the sync pulse is still set to position 12 and we're not setting it in time back to the value 45 that it needs to be. So that's just a timing issue which we can probably deal with, and it's a little bit hard to say until we try it out, but probably the flickering we see below that is just to do with the horizontal sync pulse going off in the wrong place. Perhaps when we fix that issue, that wobbling that happens below it is also going to go away. We'll see a little bit later. So anyway, there are 3 issues there for us to fix. So let's take a look at the adjusted version of linear_a.asm, where I've attempted to fix this issue. And this time we're focused on raster line 128. And the issue here was that we're trying to change the horizontal sync position back to 45, and it's currently set to 12, and we're actually not changing it in time. We're actually reaching the 12th character before we make this change. And so that means that we're actually getting a sync pulse at position 12 where we don't want one. And once again, the reason for this is the extremely long time that it takes to do our polling, this time for the start of the active region of raster line 128. So again, the solution is just to comment that out so that we save the 50 cycles and we get this sync position set to 45 well and truly in time. So that's the main change that I've made, but I decided to make one other change while I'm at it, and that is on raster line 127. Instead of making the blank scan line on the right hand side of the screen a displayed value of 0, I'm now going to make it a horizontal displayed value of 1 instead. Now this will actually give us an additional spurious character where we're supposed to have a blank scan line, but it actually ends up giving us a clue. So let's check this out and see what happens. Well, surely we now have something a bit different. And yes, this is starting to look a little bit more encouraging. We've got rid of the horizontal sync issues that we have, which is great, but it's also at the same time a little bit discouraging. We're not getting a single white scan line here. It's actually mostly magenta, which means that most of it's coming from the end of the second bank rather than from the beginning of the second bank. In In fact, we've only got one character, which is white, and that would just be the first character from the second bank. You can of course see that single character on the right hand side there, where we set the horizontal display to 1 instead of 0, and so that hasn't solved our problem. But it has given us a clue. Obviously there's some relationship between that one character that we've added on the right hand side and the single character that comes from the start of the second bank, the white part there. So I'm going to leave it with you to think about before next time, and we'll take a closer look at what actually causes this phenomena. And I have to say, at this point I'm both encouraged that we've made progress and also a little bit apprehensive as to whether we're going to be able to solve this problem. It seems that the register rights are very tight, and it may actually be quite difficult to fit all the register rights in at the right times. And so that's something we're going to look a little bit more closely at in the next video.